Today we are going to discuss about infrared spectroscopy. So first of all we have to know about what is spectroscopy. Spectroscopy is nothing but the study of spectra that is formed due to the transition of the molecule from different energy levels. So infrared spectroscopy is the spectra that is formed in the infrared region. So it is also called infrared spectroscopy is also called vibrational spectroscopy because the transition of the molecule is in from one vibrational energy levels to another vibrational energy level. That is why it is also called vibrational spectroscopy. So we all know that there is electromagnetic radiation, there is a different ranges of electromagnetic radiation which includes IR radiations, visible radiations, microwave, radio wave, etc. So this IR radiations or IR regions is again subdivided into near IR region, middle IR region and far IR region. Most of the experimental activities in case of liquid and gaseous samples are existing in the middle IR region. So for some solid sample it will experiment in the far IR region. We can see the different ranges of this IR regions. 12,500 to 4,000 centimeter inverse is the near IR region range, and middle IR region which is 4,000 to 400 centimeter inverse, and for far IR region it is 400 to 50 centimeter inverse. These are the ranges of the IR regions. So now we are going to the topic, that is vibrational energy of diatomic molecule. For this purpose we have to consider a diatomic molecule which consisting of two atoms M1 and having mass M1 and M2, and for the calculation we are consider it as a harmonic oscillator. The system of diatomic molecule considered as a harmonic oscillator. So the fundamental frequency of the harmonic oscillator is nu 0 is equal to 1 by 2 pi root of k by mu, where k is a force constant and mu is called the reduced mass, and mu can be found out by mu is equal to m1 m2 by m1 plus m2. So by solving the Schrodinger equation we will get the energy of vibrational spectra which is equal to V plus 1 by 2 h by 2 pi root of k by mu, where V is the vibrational quantum number. It can be ranges from 0, 1, 2, 3 etc. And where h is a Planck's constant and k is a force constant and mu is already said which is the reduced mass. So on substitution nu 0 is equal to 1 by 2 pi root of k by mu in equation EV. We already said that nu 0 is a fundamental frequency value is 1 by 2 pi root of k by mu, and here when we see the equation of vibrational energy which is V plus 1 by 2 k by k by 2 pi root of k by mu. So we can replace 1 by 2 pi root of k by mu here. So we will get equation of vibration energy like V plus 1 by 2 nu 0 into h, where nu 0 is a frequency in joule. So we are representing the energy in terms of wave number. So we have to get an derivation into nu 0 is equal to c by lambda. We know that frequency is equal to velocity divided by wavelength, and 1 by lambda is known as the wave number. So we are taking another frequency in terms of wave number, that is omega 0 instead of nu 0, because here nu 0 is a frequency in joule and omega 0 is a frequency in terms of wave number. So we are taking the frequency in wave number as omega 0. So the equation of the vibration energy EV equal to V plus 1 by 2 hc omega 0 centimeter inverse. In this equation we can also derive vibrational term epsilon V. It is by just dividing the equation of EV with by hc. So epsilon E equal to V plus 1 by 2 V plus 1 by 2 into omega 0. This is a vibrational term. So after solving the equations of EV, we will get a graph like this. We are drawing a graph with the energy on the x-axis, on the y-axis, and internuclear distance between the molecule in the x-axis. So we know that the graph of a harmonic oscillator is like a parabola, So we are drawing different value of V and the corresponding energy of vibration here. So for V is equal to 0, the energy of vibration is equal to 1 by 2 h nu 0. 1 by 2 h nu 0. For V is equal to 1, it is equal to 3 by 2 h nu 0. For V is equal to 2, it is equal to 5 by 2 h nu 0. For V is equal to 3, it is equal to 7 by 2 h nu 0. We can see that the energy difference is same in all levels, and these different energy levels are also equally spaced. And we can also see another thing where V is equal to 0, that the vibrational quantum number, V is a vibrational quantum number, becomes 0 at 0 Kelvin. The molecule itself has an oscillation, because the energy of oscillation is does not, or energy of vibration is does not become 0. It has a value till at the 0th level. So it is 1 by 2 h nu 0. So this energy is known as 0 point energy. So next we are going to know about the quantum mechanical selection rule for the vibrational transition. So the general selection rule for the transition is, or the spectra formation is, there is a change in the dipole moment. The spectra only form when there is a change in dipole moment. This is a general rule. So for the exclusive rule for the vibrational transition, delta V is equal to plus or minus 1. When delta V is equal to plus or minus, which means the change in vibrational quantum number should be plus 1 or minus 1. That is, we can see that the transition from the adjacent energy levels is only possible, only allowed. So that is, we can go from 1 to 2 or 1 to 0. The transition from 0 to 1, 0 to 2, 0 to 2 or 0 to 3 is not allowed. So only adjacent transition is only allowed. That is the selection rule saying. So delta V is equal to plus or minus 1. For plus 1 it is absorption, for minus 1 it is emission. So next is vibrational spectra of simple harmonic oscillator. Now we are going to look what is the shape or form of the spectra that is formed during the vibrational transition. So for that purpose we are considering two adjacent energy levels, V double dash and V dash. V double dash is the ground state and V dash is the upper state. So a molecule is transiting from V double dash to V dash. Therefore the energy change delta EV is equal to EV dash minus EV double dash. So we can write it as delta EV is equal to replacing V with V dash here and replacing V with V double dash here. So the equation becomes V dash plus 1 by 2 into h nu 0 minus V double dash plus 1 by 2 h nu 0. So we can write delta EV is equal to V dash minus V double dash into h nu 0. V dash minus V double dash 0 can be written as delta V. So delta EV is equal to delta V h nu 0. So in the case of absorption, delta V become plus 1. So here delta EV, so we are substituting the value of delta V as plus 1. So delta EV is equal to h nu 0 in terms of joule. So we can also represent it as in terms of wave number. It is become delta EV is equal to ht omega 0. We already discussed that. So the molecule is in vibration, then that time a radiation is coming with a particular frequency nu and a particular wave number nu 1. So the energy of the radiation delta is equal to h nu. This is in the terms of this is in terms of joule. So we can transform it into wave number terms, that is delta is equal to hc nu 1. This is a B equation, this is the A equation. So these two are energies. So we can compare these two energies, that is h nu 0 is equal to h nu in terms of joule. For in terms of wave number, it becomes hc omega 0 is equal to hc nu 1. So this is, we can cut off this hc on both sides, we will get omega 0 is equal to nu 1. So which means therefore a molecule is already in vibration with a frequency omega 0. Then a radiation is coming with a wave number nu 1. So the transition, the vibrational transition is occur only in the case that the frequency of the oscillation omega which is equal to the wave number. This is the condition for the transition of the molecule. So this is it, and this is the form we can represent the spectra of this vibration. and the spectra will be in this form. We can obtain a single line spectra for this absorption or emission, because we already seen that the energy gap between these two lines, every energy levels is same. There is no energy differences between these two lines, only same energy is existing in every line, and each energy levels are equally spaced. So, for every transition we will get a spectral line at the same position. That is the spectral line that is formed in the absorption or emission and the vibration transition. Thank you.